He's
Okay,
ready.
great. All right.
Our presentation today will be focusing on the GO-LSTM-Kriging model on the Georgia Tech campus. My name is Tanasan, and I am presenting this on behalf of our team, which include Chris, C, and Sophia. Our project and Abigail. Yeah, our project was guided by Dr. Kastner. This work explore the integration of machine learning, GO-LSTM, Kriging model, and Kriging technique to analyze urban microclimate on our campus. Next slide, please. First, we will discuss the effect of urban microclimates, emphasizing how they influence campus environments. And next, we will introduce the GO-LSTM Kriging model, explaining its structure and purpose. Then we will go to the methodology. Finally, we will share our reproducing results of an existing model developed by NUS and adapting it to the Georgia Tech campus. Next slide, please.
Okay, thank you. And sorry for those who were here last semester. This might be a repetitive background, but it's just as applicable. But yeah, urban heat, it's not a foreign subject to us. We see countless articles, media, etc., everything you see here on the screen in front of you about rising temperature experience in urban areas. And we ourselves get to experience it in real time, and we feel it even more as the years go by. And so urban microclimates occur as a result of this spike in heat, where they have different local climates compared to their surrounding areas. And this can have incredible negative effects targeting various dimensions of our lives as well as of our environment. Things like increased health risk are experienced as a result of these rising temperatures. It also changes the way we occupy space in urban areas and also our urban mobility. And more so, it also increases building energy usage, which is not only expensive monetarily, but it's also expensive and taxing on our environment. So being conscious of these results in urban heat islands, it brings us to wonder how we can make our spaces more habitable, keeping in mind how our buildings affect our urban microclimates. And so shown is a classic example in a city familiar to us, in Paris, France. The map on the right shows the temporal averages in the summer months of May through September. And two, I'm not sure if you can see my cursor, two weather stations were used, one taken in the heart of Paris and then one further out, more in a rural part of the city. And we can see a very drastic temperature difference, about a 5 degrees Celsius difference from when you're in the heart of the city compared to further out. And this, again, is just uncomfortable, unhealthy, and is something that we'd like to change or even avoid if possible. And so like Dr. Kastner said, last semester, this team dove into the urban weather generator, which is a model developed by MIT as a potential one for looking into modeling the urban microclimate. But we wanted to pivot to something closer to a surrogate model, since that's what our VIP focuses on. And so we decided to look into a deep learning model developed by the National University of Singapore called the GO-LSTM-Kriging model. And this model incorporates both spatial and temporal dimensions, as well as land use, land cover, or LOLC data, bringing a new approach combining all three for microclimate prediction. And it's applicable for fine-scale prediction of the area about a few hundred meters surrounding the weather stations used to collect this data. And the name is long, so to break it down, the geo layer processes and learns from the land use, land cover data. And the LSTM layer learns from historical data, taking recurring patterns into account, while the Kriging layer extracts spatial distance information. And so combining all three outputs, in theory, accurate results with higher spatial resolution and at a quicker speed. So Krish is going to take us into the steps we took to integrate and adapt this model, as well as our data for the purpose of studying microclimates.
Yeah, so for our methodology, we had three workflows. The first one was pre-processing, and then we had ML training and prediction and plotting. So pre-processing, which is the one I was mainly involved with, it involves cleaning up the data, just making it really, making it usable for the ML training and so that we can actually use it. I was doing pre-processing for the spatial prediction method that we were using. So I took the map of tech, and with some help, we overlaid equally spaced points. It was a grid system on top of the map. And then for each of these points, I'll get more into like some pictures of this in the next slide. But using these points, I then found the nearest distance to trees, buildings, fitness centers, many other variables. And using these vectors that I found, we then used the Kriging spatial interpolation technique that Sophia just brought up. And this helps us figure out the temperature values at unmeasured locations based on the surrounding points that we already have. And then we have the ML training, which incorporates the temporal prediction model using the LSTM long short-term memory model. And this is what will give us the actual temperature graphs that we'll see on the next slide. So if we could just move on. Yep, thank you. So here we have the pre-processing for the spatial data. So if you look to the picture on the left, you will see that there's a square grid, and this has multiple equally spaced points. And from these points, we then have a bunch of distance vectors. So the variables I used were obtained from OpenStreetMaps, which is a Python library. And I was able to get locations and distances to buildings, parks, libraries, parking, footway, grass, fitness centers, woods, and wetlands. So that's 9 variables. And the more vectors we have, the more spatial interpolation we could do. So we also wanted to add tree information, and we were able to get the tree information from GT's Tree Viewer app. And one of the outputs of pre-processing is a CSV file. And if you look at the CSV file on the bottom, which is that Excel table, you will see the actual values for the distances and each of the locations of the points. So this is what goes into our ML training model. And then Z is going to take it from here and talk more about the ML training and how we obtain the results.
All right, thanks, Chris, for getting us started. So now let's talk a little bit more about the actual data that we're using, that we're applying this model to. And special thanks to Professor or Dr. Brian Stone for providing us some very nicely gathered data captured on the Georgia Tech campus. In the past few years, he set up many weather stations across the campus, and they pretty much have them active for over about like a year, and we're able to get some very nicely measured data or weather data from the different parts. Mainly, it gives us a lot of information about the temperatures, relative humidity, and dew point data. So this will be the main thing that we're trying to predict using this model or being applied to our campus. So firstly, we got started by cleaning up the data, as the data we got were actually pretty messy. And we began by formatting them into properly or usable ones, such as CSV files. Of course, special thanks for Patrick for helping us with the cleaning part. And here, I gathered the different coordinates of the various weather stations on campus, as well as separate them into their own individual or into folders. And as you can see here, we have the locations that is respective to each of the station ID right here. And we begin this by doing a little bit of extra cleaning by filling up the none data types within each of the weather station files just by taking the mean or the average of each of their respective columns, namely the relative humidity, dew point, as well as temperatures. We do some normalization so that to ensure that in training there will be any sort of conflicts or any sort of, I guess, errors that could come up with predicting different values. So we normalize them into 0 to 1. Then afterwards, I separated or essentially appended each of one of them into a dictionary, because originally I tried to train the weather station files in one single large data set, but of course that is way too much for my computer to handle. So splitting it up to dictionaries ensured that it was able to run very smoothly. All right, next slide, please. Wait, not sure why the pictures aren't showing. Can we refresh or? Because this is like the outdated version of the slide.
You might have some animations on the slide. Maybe you have to go one step further.
Sorry, let me just try and open it again.
Yeah, because I did add a few pictures for.
There you go.
All right, cool. So now let's get more into detail about the actual LSTM code. So of course we define the function for LSTM. It is of course in PyTorch. And here we set our main features for prediction as the relative humidity and the main features as a relative humidity and dew point, and our main target for the prediction as the temperature. We create the sequence for the LSTM to and set it as the default 10 time steps. This is just based off the default values. We haven't really tried playing around with the specific parameters yet, or tuning it, but usually this is what the documentation recommended. Hidden size set to about 8 layers and about 200 epochs, which epochs are just how many iterations you want the program to run through the training again. So this just ensures that, okay, our program is decently well-trained, not to overfit it. If we were to set even more layers in epochs, then it could definitely lead to overfitting if we would have provided with a new weather data file, but this is just usually the default settings for that. All right, then afterwards, wait, actually, can we go back one more? Then we can talk about the next part. So we train each of the weather stations file individually. Then finally, we append them into one single data frame to get the average prediction results for each of the stations. And now let's go on to the next slide. And here, this is where we start doing the actual geo-Kriging model. These are these spatial features that we gather thanks to Krish's grid point dataset. As you can see, it has all the different distances, distance data for each of the grid points as we generated. There are about 1,300 different grid points generated for this dataset, and each of them contains specific measures for distance to buildings, parks, trees, wetlands, etc. for our campus. And we set these as the values for our coordinates and prediction in the Kriging model right here. And of course, the Kriging model is based off the random forest regression, which is the main choice for this one because random forest typically works well with a lot of different types of parameters, and especially if our data comes out to be nonlinear. So then we finally fit the model with these parameters and then showcase the final result in the next slide. And as you can see, this is the results that we've gotten for Georgia Tech campus. For the most part, it seems to be relatively accurate, I would say. There are a fair bits that are a bit confusing as based on the grids, we can see that okay, towards the area in Midtown, there is a much higher increase in temperature, but towards the bottom left is mostly like a very there's a very there's a lot of vegetation and it's like a pretty regular neighborhood. So that part I'm a bit iffy about as we compared with the map on the right over here. And each of the grid points here are the respective weather stations along with their average values. So that's pretty much it for the results that we've gotten for this model. Definitely, there are to go into to conclude essentially this research. The Kriging model or LSTM Kriging model is very interesting because it does take a novel combination of LSTMs with creating spatial data, which hasn't really been done before. Many other attempts have, or other surrogate models really just rely on regular time series data and haven't really explored much of spatial data. It does appear to handle much larger data sets with better results, as the original research did run this model with about 1 million grid points. So if we also have access to that large, we could possibly be seeing much better results as well. But due to time restrictions as well as the computation we required, we weren't really fortunate enough to get a data set of that large. And then, of course, features can be tweaked for personal preferences. These are only just the 9 vectors that we looked at specifically from the ones that we gathered. Of course, there are a lot of different types of features that we could potentially explore, such as like different multi-scale spatial features, buildings, and many of other parameters that I can't really think of from on top of my head. But there's definitely more room for improvement in that way. Now on to some cons. Some of you guys might remember, but I did spend a lot of time cleaning up the GitHub repository for this code. Unfortunately, the people at NUS did not provide a very user-friendly or legible code to read. So I spent some time cleaning it up and made it as straightforward and runnable as possible. So I guess that's a con, but not necessarily catered towards the model itself, but just something to mention. Of course, training larger data sets is very computationally expensive. Just training our current data took my computer about like 20 minutes of running with the parameters that we set. And if we were to train it with a much larger data set, containing more weather stations and maybe even weather stations that contain data throughout the year, because it's also more noteworthy that the data we got from Dr. Stone only had about 2 to 3 months worth of captured temperatures. And if we were to focus on yearly results and across like an entire span of like maybe 5 to 10 years, then yes, it would take much longer to train. But it is also noteworthy to mention that once you've trained a model, you can pretty much just save it as a PyTorch file, and it will run very smoothly afterwards. It's just getting it trained in the first place. And then the same could also be said for just tuning the parameters. I did try out or try writing an optimization method for just figuring out like what is the best input for each of the parameters, and I couldn't run out my computer. It crashed before it finished running. So I could only assume that it does take a lot of computation power, and we would have to try it on the HPC in the future if you want to improve this model or fine tune it better for better results. And of course, possibly the biggest con to something like this is that it is a black box model, which means we don't really understand a lot of the math that's happening behind the scenes for a lot of the machine learning models, and that could come into some or bring some issues with public policy communication, because when you're communicating with these urban decision makers and you're telling them essentially, okay, well, we have this model, we know it's accurate, but we don't really know how we got its values from, then it could be a little bit difficult to bring about rhetoric or make a convincing argument that this model is indeed trustworthy. But that could, of course, be mitigated if we go into a more deep dive with like the theory behind LSTMs and neural networks. And then, of course, like going into more potentials for improvement. Yes, adding some sort of multi-scale spatial feature to the features for prediction could definitely improve its accuracy, or there are maybe some other parameters that we haven't really looked at yet. Some sort of interactive and visualization tool could be very helpful for people who would like to experiment with this model since it's shown to be decently accurate. Maybe some sort of plugin for Grasshopper or something that lets us play around with the parameters without directly going into a code editor, like just like the Urban Weather Generator had with its own plugin for Grasshopper. And of course, this leaves us some room to explore other model combinations, like such as what would happen if we were to use CNNs for predicting the maps generated, or getting like a pretty accurate generation for the maps, or maybe instead of doing the Kriging method or Kriging regression, we could try using graph neural networks to represent stations as individual nodes and finding the interpolations that way as well. And that pretty much sums up this project.